Welcome to Artificial Neural Networks, the idea behind modern AI. Let's dive in. Hi there, let's learn neural networks the easy, visual way. We'll see what they are, how they learn, and where we use them. No scary maths, just simple pictures and ideas. Ready? Let's begin. Here's the big idea. A neural network learns from examples. We hand it something, say, a photo of a cat. The picture becomes numbers, they flow through the network, and out comes an answer. It's a cat. Show it enough examples, and it learns the pattern completely on its own. Where did the idea come from? The brain. Inside your head, billions of neurons fire and pass tiny signals to each other. An artificial neuron copies that idea with numbers. Signals come in, the neuron adds them up and fires, and a result goes out. And they're everywhere today. Neural networks recognize faces and objects in photos, power voice assistants that understand speech, translate between languages, and suggest what you'll enjoy next. Anywhere there's a rich pattern to learn, they shine, quietly working behind the scenes in the apps you use every day. So let's look inside a single neuron. Each input arrives with its own number. The neuron multiplies every input by a weight, how important that input is, then adds them all together, plus a little extra called a bias. Finally, it passes that total through an activation function. That's the whole recipe. Now let's watch it happen. 3 inputs flow in. Each one is multiplied by its own weight, some positive, some negative. We add the results together, then add the bias. That total is squashed by the activation function, and out comes the answer. 0.62. Multiply, add, activate, that's all a single neuron ever does, but together they become powerful. That last step, the activation, deserves a closer look. Here's its S-shaped curve. A big negative number gets squashed close to 0, so the neuron stays quiet. A big positive number is pushed close to 1, and it fires. Whatever goes in, the output always lands neatly between 0 and 1. One neuron is clever, but the real power comes from stacking many together into layers. First, the input layer where the data enters. Then one or more hidden layers where the real thinking happens. And finally, the output layer which gives the answer. Signals flow steadily from left to right, layer by layer. This left-to-right journey has a name, the forward pass. Let's follow it. Our cat photo enters as numbers at the input layer. The first hidden layer combines those numbers and passes its signals on. The next layer combines them again, picking out more and more useful features. Layer after layer, the signal travels forward until it reaches the output. And the network announces its verdict. Cat, 92% confident. But how does it get good? The secret is the weights. Every connection is like a little knob. Turn them one way and signals strengthen, the other way and they fade. Learning just means finding the right setting for every knob. So how does it find them? Through a simple loop repeated over and over. Step 1, make a guess. Step 2, check how wrong it was. Step 3, adjust the weights. Step 4, repeat. Each time around, the guesses get better. Let's walk through that loop. First, the network makes a guess. It runs a forward pass and leans toward dog, 65%. But the true answer was cat. The gap between the guess and the real answer is called the error. Right now it's large because the network hasn't learned anything yet. Measuring this error is the key to getting better. Now the clever part, backpropagation. We take that error and send it backwards through the network, from the output back to the input. As it travels, each weight discovers how much it added to the mistake. A weight that pushed toward the wrong answer is nudged down, one that helped is nudged up. Every knob gets a tiny adjustment. This backward flow of the error is how a network truly learns, bit by bit, mistake by mistake. One adjustment isn't enough, so we repeat many times. We show the network example after example, and each full round is called an epoch. Watch the error. Round after round, it keeps falling. And the guess on our photo sharpens too. The network grows more and more sure it's a cat, climbing toward 95%. Slowly but surely, it's learning. Let's see the payoff side by side. Before training, the network is just guessing cat or dog, almost a coin flip at 50-50. After training, shown the very same photo, it's confident and correct. Cat 96%. Nothing about the picture changed, only the weights inside the network did, and that is the power of training. You'll often hear the term deep learning. It just means a network with many hidden layers. A shallow one has a single layer. A deep one has many. More layers let it learn richer, more complex patterns, and that's exactly what makes deep learning so powerful. There are trade-offs. Neural networks are brilliant at complex patterns, superb with images, speech, and text, and they improve as you feed them more data. But watch out, they need lots of data, plenty of computing power, and they're hard to explain, a real black box. When should you reach for one? They're perfect for images, sound, language, and rich, messy patterns. Skip them when your data is tiny, when you need a clear explanation, or when a simple rule already works. Let's recap. A neuron multiplies its inputs, adds them up, and activates. Stack neurons into layers and you've got a network. Learning means tuning the weights, guess, check, adjust, repeat. And with that, it can recognize patterns all on its own. Thanks for watching.